Hello and welcome back to this next video in the series of videos that we're making here. We are continuing with the 6502 repeater project. We've already created the schematic diagram in KiCad 8, KiCad version 8 now, and we migrated from 6 as you've seen in the previous video. And we're pretty much ready to go for the PCB design. At the moment we have no PCB layout or anything, there's no tracks, there's no nothing assigned, so we're going to start by looking at component footprints. And what we mean by that is, if you have a look at some of the components in the schematic and you double click them, just a double click there, you'll notice that we have a reference of U1, we have a value of an LM324 in this particular case. I've just chose a component at random. You just got to start somewhere. But the important thing is, you'll notice that this box here, footprint, is empty. And that means that PCB Designer will not know which layout to use, how the pads are going to look for this particular chip. Now, an LM324, there's a couple of variants of it. You can have a DIL, dual line version, you know, your standard through hole type PCB mount. Or you could have a surface mount version of it, which would be what the class is a SOIC footprint. So we can go for either surface mount or we can go for a dual inline package. We need to make a little bit of a decision on the whole project here, because there's two ways we can go. We can go standard through hole components, which will make the board a little bit bigger, but that's fine because we've got plenty of space. We could also go for complete surface mount, or we could go for a hybrid between the two. I'm sort of thinking more surface mount. It's not really a retro project anymore if you think about it. I mean, you know, we've got a microcontroller in here, you know, which could probably handle all of the functions of the repeater if we wanted to, in one chip if we actually wanted to. Yeah, it's just more of an academic exercise to have a 6502 controlling all of this on the controller card. I think it's fine. We're not really trying to make this completely retro anymore. We just need it to work, really. I think we're going to go for surface mount, and it also means when we come to solder up the parts, it'll be interesting, I think, and I'll show some of the parts being populated and soldered to the board in the final result there. So let's look at the LM324 again and double click that. Go back to the footprint setting. So really what we want is a SOIC, SOIC or something similar to that. We can open up the library explorer, which will take a moment, and we'll do a jump cut while it loads. Okay, and now we're back. It's the first time I've loaded the footprint library on starting my computer, and that usually takes a while for it to load in, but once it's loaded in, subsequent opens should be much faster. So let's look at the footprint for this chip. Now what I'm thinking is it's probably going to be, let's try SOIC, SOIC, and we need a 14 pin because that's what the chip is. So let's have a look. That's a SOIC 8. So we need to figure out whether we want the wide space or the standard narrow. Pretty sure it's this one actually. So let me just measure a chip and make sure we get the exact right size that we want. So that's SOIC-14 underscore 3.9 times 8.7 millimeter. Okay, so that's actually the size, and that's what the footprint's going to look like here. 3.9 by 8.7 with a pitch P, if you like, 1.27 millimeters. Let's click OK to that. Right, so you'll notice that that's now gone into the footprint. And there's our SOIC 3.9 by 8.7 millimeter. Let's click OK to that. And let's progress to some other parts. Well, what about the 4066 chip? Now it's also going to be on a SOIC. It's going to be exactly the same footprint. Now what I can do is, instead of searching for it again, we can copy the footprint from here, like that. Control C, standard copy, close that, and we can simply open up a 4066 here and drop it in. Control V, paste it in. There you go. So that's now going to have the same footprint. It is also, of course, a 14 pin chip. So that's correct. You'll notice I'm sort of doing the active components first. There's no real method of the right way to do this. You just work your way through. I tend to get the active components, you know, like semiconductors and stuff, out of the way first. The thing is to end up with all of the components having an assigned footprint, which is what we're doing here. So let's check our little keying transistor. Now it already has a footprint. That's good. And it says it's going to be a THT, a through-hole SOT TO92 in line. So it's going to be a standard transistor package rather than a surface mount. Now there's nothing to stop us making a surface mount footprint for that keying transistor, but I'm actually going to leave it as a through-hole type device, because if we ever get a problem with it, if it blows up for instance, if we have a problem with the transmitter or anything like that, we can easily replace that. The other thing you'll notice is these capacitors are actually electrolytic, and they don't need to be. We can make these multi-layer ceramics, SMD, surface mount. We can actually replace, we can get 2.2 microfarad, no problem at all. So they don't really need to be polarized electrolytics. That one possibly could be, maybe leave that as a polarized. But these certainly don't need to be. They can be ceramics. So sticking completely with multi-layer ceramics, just because they're very easy to work with. You can put them, obviously they're non-polarized, you can stick them in any which way around you like. It's less to go wrong, and they're also a bit more reliable as well, with a better ASR generally. Let's just pick a resistor. You'll notice again we've got no footprint here. So let's pick something for the footprint for that resistor. Well, the series of resistors we're going to use, because we said we're going to go surface mount, it's probably an 0805, a 0805 size. So let's type 0805. Capacitors, diodes, fuses, inductors, resistors, there we go. So it's going to be something like that, 0805. It's also classed as a 2012 metric. And there's a version here which is, it says hand solder. If you'll notice, those pads are slightly smaller than those pads. You see the red size here. When we go to the hand solder version, you get a little bit more area to solder to. It is exactly what it means. It just means it's easier to solder by hand. You get a little bit more area to play with your soldering iron tip. So I'm going to select that. And we're going to copy that, because we've got a ton of resistors. Copy that, and we're going to just literally drop them in. So let's click OK. Okay, so that's our first resistor done. What about this one here? Again, it's going to be an 0805, so I'm going to do Control V and just drop that in. There you are, done. See how quick it is now, because it's in the clipboard. Footprint, Control V, done. Footprint, Control V, done, and so on. Control V, done. And I'm just dropping in the correct footprint sizes. We're telling KiCad these are 0805 resistors, surface mount, so it knows what the footprint looks like when we come to do the PCB design. So there's all the resistors done there. Let's do some capacitors. So again, it's an 0805 size, what I think we're going to aim for. So let's go back to the library, type in 0805. 0805 is a decent size, pretty common and not difficult to solder, as we'll see later. So let's scan down for a capacitor, there we go there. And just like we did with the resistors, 2012, and we've got 2012 metric hand soldered. And if you look at the size of the pad when I click this, ready? See I go bigger? It's probably even the same pad, except this time it's for capacitors. Probably the same footprint. Let's select that, and again we're going to use hand solder. As I said earlier, it just makes it a little bit easier to solder by hand. Click OK to that. Let's try that one again. Yeah, and there's our footprint here again. Now of course I'm going to copy that, so I'm going to do Control C, copy that. Alright, and we can drop those into these capacitors here. They're all the same. Footprint, Control V. Okay, open that one, footprint, and I'm just double clicking those, by the way. Control V, drop them in. So there you go. I do believe all of the components in this section are now allocated with PCB footprints. Let's do some more capacitors. These are all 0805 capacitors, so I'm just going to quickly go through these, double click, and we'll fill a few of these in. Okay, you know, and so on. Those are done. That one's done already. That isn't done. Put him in there. He's done. And so on. Now I'm not going to go through the whole sheet. What I will show you is the microcontroller footprint. So let's open up that one. Now you'll notice we've already got a footprint. Okay, we've already got a footprint on this one, which is great. Because we've picked a specific component from the list when we did the schematic, it knows it's a TQFP and it knows it's a 32 pin 7mm by 7mm with a pitch of 0.08. So it knows what the footprint is. That's great. It saves us having to go through the footprint library. So that's good. We've got a DIL header here. You can get surface mount dip switches, not a DIL header, sorry, a dip switch. You can actually get surface mount dip switches, but I'm going to go through the through hole version. They're just bigger, they're just easier to solder, and you know, we've got plenty of room on the board. We really don't have to make anything micro miniature here. So let's look for the footprint for that. Open up the library and I'm going to type in dip switch. Does it know what I mean by a dip switch? Yes, it does. Now what we need is a 6 position. Okay, so ours is a 6 position. That's a 2 position, 3 position, 4 position, 5, 6. That's a piano type, where it's got like the little levers on the side. Now you could actually use that. That's nothing wrong with that. Piano style again. Slide switches. Now these are your classic top adjustable switches, and this is kind of what I'm aiming for. So let's select that, double click it. There you go. So that's now got a footprint allocated to it. We haven't actually got to populating all of the parts, and if we try to create a PCB now and it's not finished, so I'm going to click this icon up here which opens up the PCB Designer. You'll notice it's now 806 and it knows we're going to design into revision 1.1. So we need to click this icon here which updates PCB from schematic. So this is going to load in as much as it can from the schematic onto the PCB. So let's click that. It's tried to do that, but you'll notice there's 35 errors. There's 0 warnings. That's a good start. But there's 35 errors. A lot of the parts were added, and these will be the ones that we've done so far. There's our 0805 footprint for a capacitor. There's our 0805 footprint size for a resistor, and so on. You know, there's our transistor there, our keying transistor, TO92 inline. So a lot of them's been done, and then you've got these where J3, J4, R3, R4, these are not added. I'm just showing this in case you get to a situation where you see these errors. It means that the footprint, as it says no footprint assigned. It's telling you that we're not really ready to start putting the board together yet because we haven't assigned all of the footprints. So best thing to do here is just close that, back to the schematic. Now what I'm going to do now is I'm going to do a jump cut, and I'm going to rattle through this. Probably take us about 20 minutes, and I will add all of the footprints to every component I can find, including the connectors. These are going to be headers that we can connect to. Okay, and we're back. Yeah, it took about 15 minutes, something like that. So anyway, I've gone around the sheet and just made sure everything had a footprint. As I say, most of the resistors and the capacitors were already done over there, and we added a few down here. I've gone ahead and done everything else, so we've now got footprints for all of the components. After we've got all the footprints assigned, open up the PCB Editor, which is this icon here. So let's click that, and it loads up our default board with nothing on it. And you'll notice this is our PCB here, dialogues here, and it's waiting for us to do something. So the next thing to do is to load in the all of the footprints from the schematic that we've just completed. So to do that, we need to go up here and click this button here, which is Update PCB from Schematic. You can also press F8 if you wish. I tend to just click the icons, but there you go. So let's do that, and it will load in all of the schematic data. Now, if you've got a problem, like I said earlier, it will show up here as something doesn't have a footprint, or it's the incorrect footprint for the component. You'll notice down here, we're all good. we've got 0 errors and 0 warnings. Now don't forget, this is not the same as the ERC, which is the electrical rule checker. This is checking for footprints and for the PCB design layout. So this is a DRC, okay, design rule check. It's a different check. It looks like a similar dialog, but it's not the same. Okay, so we're good. It means we've got all the footprints in. Let's click Update PCB. And now we end up with this thing here, which is like a big chunk of components, and it puts it in some kind of block. And what I tend to do is stick it to the side somewhere outside of the sheet size, and I'll just drop it there with a left-hand click. So there it is there. And there's all of our components. You'll see there's all the variable trimmers. There's our keying transistor, 14-pin SOIC chips. One will be for the LM324 and the other one will be for the 4066, and so on. There's our header. Got a 16 megahertz crystal with a small footprint for that. That's through hole rather than a surface mount crystal. That's the footprint for the 32-pin Atmel 328P. That's going to be the CTCSS decoder. I've got a 4001 diode here as part of the keying circuit. Again, you know, that could easily have been a surface mount version. Doesn't really need to be that big. But the reason why I'm doing this is so I can replace it easily if anything gets damaged. The same with the keying transistor. We've got a fuse on board, which is going to be a circular bodied fuse, 2-pin obviously. And there's a whole bunch of resistors and capacitors there, which are all, looks like a right old mess. But what we're going to do is we're going to move them all, everything around, and get everything on the board where we want it. Let's say if you want to move the header, and in my head I've already got the header on the right hand side of the board somewhere along with the power. So I'm just going to select, you just click it there with the left hand mouse, and you can drag the whole component the way you want it. So it's going to be up there, something like that. What I'm going to do is spend a bit of time, move these components around where I want them, and you can drag them around to the board design. It needs to go in here, and then, you know, take the components one at a time, probably put the, I'm just guessing here, and the switching. Now what you can do is you can look at the rat lines and you can go, okay, maybe I want to rotate that the other way, and just try and avoid too much crossing. Sometimes it's a bit difficult to say. Just get a feel for it, you know. Do I want to put it sideways? No, that's not bad. Can you see that? It's kind of like all the tracks are sort of like in parallel there. They're running along each other. If I turn it around here, now you see things are crossing. Just get a feel for it and sort of go, yeah, that looks like it might be, you know, not too much track crossing. That makes the Autorouter's life a bit easier. Should be a bit quicker. Do I want to turn it round? It would be nice if it was sideways, but now you can see all the tracks are crossed. It's not so good. That's completely crossed there. That's all right. That doesn't look too bad. Yeah, you know, you could kind of go with something like that. That's not too bad. There you go. Because these are all going to be grounded. All of these pins are going to be grounded, and these ones go to the chip pins themselves. So that's going to be routed through. And, you know, you just sort of move things around, just get a feel for it. Now what we can do is flick backwards and forwards between the schematic and the PCB layout, and this is very handy. I'll show you this. So if you click on this icon up here, switch back to schematic, right? Now we're back to the schematic. There's our crystal that's selected. You notice it's highlighted because that's where we just were. Now I want to highlight these two capacitors because I want to stick these in next. C18 and C19. By selecting them here, if you go back to the PCB Designer, which is that switch to PCB Editor again, you'll notice these two have gone pink rather than the standard red. And that means that these are selected. Now that's great because I probably would have had a hard time finding those, and that means I can drag them, both of them, to the crystal. And probably put that in there somewhere, and you'll notice that's the rat lines are kind of going the right way. That's a good sign. We could put it in here, we could put it in the middle, nothing wrong with that at all. Might even be better, just means I'm going to have to move the crystal slightly further away. I'll separate them just so we can see the legend a little bit better. Right, there's C18 and there's C19, and we've made a start on our PCB layout. Now obviously as we go, you know, things are going to change. I mean, it's always the same. I mean, they will. We're going to keep going, move everything to the board, get everything in the right place, and I'll do a jump cut, and we'll do that right now. Okay, so I've gone ahead and added a lot of the components to the PCB design here. As you can see, if we zoom out, you'll notice I've got no spare components. I've actually managed to drag everything onto the board. Just personal preference, I like to have connectors on the right hand side. It could have been along the top, it could have been the left, it could have been along the bottom, it could have been in different places altogether for the power and the card connection. I don't really want to push this project too far for minimization, but I'm just saying there are things you can do to really try and condense the whole board, the whole, if you like, the whole project, the two boards connected together, trying to make them as small and compact and put it in a plastic box or something, or into a small metal box. I'm not really going to go that far. You'll notice we've got like a fair amount of gap going on here, and really it's not being used for anything. I may put some legend in here, some text. We may want to make physical changes to the board later. We might want to change component values perhaps. You know, it is a prototype still. Let's say hopefully a working prototype, put it in a box at the end of the day. So I don't want to compress the components like too close together. So now we can drag this whole area. This whole area here is the whole CTCSS circuit. So that can, well, it's the microcontroller part of the whole circuit. Sorry, it's not the audio part. And we can drag that, maybe drag that into there a little bit, and reduce some of the gap. And all I'm doing is just like shuffling components around a bit. This can now come up a bit. You see that? That's clearing up the bottom. So I'm just reducing the gaps without going too ridiculous. I don't want to go too far, like I said earlier. So what you can do is get hold of the, this is an edge cut, by the way. You'll notice on the right hand side you've got this here, which is edge cuts, and that is a rectangle, just a rectangle box of layer edge cut, and you need that to define the outside of the PCB. So all I'm doing here is selecting this and just bringing it in. What I haven't added to the board yet are the mounting holes. Probably going to have 4 mounting holes, 1 in each corner, just so you've got somewhere to screw the board down to something. So roughly what we've got is our card connector here, power connector up here, and a fuse, keying circuit here for putting the radio into transmit, that's the keying transistor. We've got some variable resistors up here and U2. And don't forget, you can highlight the component like that, just click it, and then we can go straight to the schematic, switch to schematic. It will show you, and there they are there, what we're actually looking at. It's a 4066, and you can go back again. Well, actually, if you deselect all that, let's say we wanted to look at the CW mute control. Where is that on the board? So you just like left hand click and select, press the PCB editor, and there it is. You see how it's kind of like different to the others? That's going to be the CW mute control right there. So you can identify things by flicking between the PCB editor and the schematic editor. This is our V-mid circuit here. This is going to create the V-mid from the positive rail, if you can visualize that. This is the LM324, which is, this down here is basically the passive components for the low-pass filter. The signal from somewhere, from one of the connector pins comes in. It looks like it's this blue one coming right through here. Is it, or is it not? Might be. Yeah, comes all the way through here and goes right to that connection just there. Passive components, which is part of the low-pass filter. Again, I'm going to move things around a little bit. I've also got here this is part of the phase shift oscillator. You've got 100N, 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 and a few 4.7Ks. I've purposefully put them in these positions, so if we need to do any fault finding or anything, you can see it sort of follows the schematic. One of those and go to the schematic, it will take us there, and there it is, there's the capacitor there. It's kind of following this part of the circuit really. Okay, so that's handy. So yeah, that's really coming together. Now you can see we've got gaps here. I could probably drag all of this section here in You see that? And we can really, I don't want it too close to the 16 megahertz oscillator. It means I can bring this in now. See that? Make the board a little bit smaller. Click save. Yeah, we're getting there. Still quite a lot of dead space down here. We could probably take the switch, rotate it, and stick it in there. I mean, we could do that. But can you see how these rat lines are now crossing? And that's going to be a problem. So rotate it again twice, and now they're not crossing. See that? For that, and it means we can bring the edge connector in as well. Bring that right in. Ooh, look at that. That saved a bit of space. So as we go, the board is getting smaller and smaller, more and more compact. There's still plenty of room for maneuver here. There's still space here. I could probably take all of these. Let's try that. Oop, I've dragged too many. Select them. That can actually fit in there. I mean, it really could. So what we can do now is have a 3D view of the board. Now, not all of the components have got an actual picture of the component. Some of them do, some of them don't. But you can still see where things are going to be positioned. So let's have a quick look at that. From here, from view here, you can select 3D viewer, or Alt 3 if you like. So I'll just do that. And there's our board so far. Yeah, there's quite a lot of space. Like I said, you know, we're not trying to push this too far, but I can clearly see that these components here could be like moved right, and that will give us a bit more of an edge there. Probably pull things in a bit. So there's our chips. Okay, there's a chip there, there's a chip there, and there's the microcontroller there. Connectors, and this is where the trimming resistors will go. Of course, there's no pictures for those, unfortunately. I think we've got pictures for, oh, we haven't got a picture for the fuse. So I'm just going to rotate the board, and you can sort of see it. You've seen this before in a previous video, and probably lots of other videos. And if you look at the back side of the board, you'll notice we've obviously got no tracks yet, but we've got plenty of holes for the components. And I think it looks great. I love the 3D view. It really gives you a feeling of, you know, where things are going, where things are located. There's the dip switch there for the programming. There's our LED. That's gonna come on when we get a detected tone. J1 is our serial comms TX-RX for future expansion. The next thing we need to do is really think about getting everything joined up. Now, like I said earlier on, there's two ways we can do this. We can actually do it manually, which is completely fine, and to be honest, it probably wouldn't take too long to do that, or we can use the Autoroute. And I know there's a lot of discussion about which way is best to go. Some people can't stand using Autorouters, and other people think they're the best thing ever, so there's a lot of discussion about it. I think we can Autoroute this, and it'll probably do it in about 5 minutes and it's done. So I think that's what we're going to do. I'll just take a break, do a jump cut, and next we're going to do some Autorouting. Okay, so to get started, if you want to use Autorouting with KiCad, it used to be a little bit difficult, and you had to, as I've explained in a previous video, you had to download a Java file, and then you had to put it in a particular place, and it was a little bit convoluted to try and get the thing to work. They've made it a lot easier now. If you go to the KiCad start window, if you go to Plugin and Content Manager and click that box there, this basically opens up the Plugin and Content Manager. You can find Auto-Routing plugin in here and install it directly. Now you'll notice I've got a tab here called Installed, because it's already in my case, but there it is. So that's what it looks like. And if you click on that, it will show you some information about where the file comes from, some version history here. It's up to version 2.0.1. It does require the Java GRE engine, which you can download from here, adoptium.net/temurin/releases, and you can get it from here. That's where you can get the version of the Java GRE 17, which you need in order to run the plugin, because it is written in Java. And you can click that and it'll take you straight there. Let's have a look. It takes you to this page here. You can download in various formats. So PCC 64, 64 architecture, x64, which is what I'm using right now, and you can download all this kind of stuff here, different versions. There are Windows versions where you can actually download the MSI, and if you download the MSI, it's a complete installer, very easy. Just follow the menus and off you go. Like I say, there's Mac OS, of course, and there's got to be, yeah, plenty of Linux versions as well, so it covers all the different I'm using x64 Windows, so that would be mine right there in my case. Anyway, it's already installed on my machine, but that's how you get it. So with the GRE installed, plugin installed, you should be good to go. And once you've actually installed the plugin, it appears up here. And there he is. That's the free routing Autorouter right there, ready to go. So let's give this a try. Our first attempt. Haven't actually done this yet, so this will be interesting. And I'm going to click the free routing plugin button at the top there. Let's do that right now. And it will execute the Java application, free routing. And here we are. Here's the free router. Oy. Now what it's going to do, it's going to automatically start. And I'll just drag this to the screen. And there it goes. I haven't clicked a single thing. It just did it automatically. One thing you can do with autorouters, before you run the autorouter, you can set up classes of track widths. And you can tell it, for instance, that you want the positive rail to be thicker than all of the other traces. So you can do all that, and you can, oh, it's done. That was it. Took about, I don't know, 20 seconds. How long was that? If you set up your classes, you can actually set up class widths. I haven't done that yet. Probably will for the final design. But just to let you know, yes, you can do that. Free routing actually obeys those classes. So if you do it in your design, and when you put it through the router, the tracks will actually follow the the track widths that you want, which is really handy. So I'm just going to have a look around, see if there's anything obviously glaringly bad. I mean, there are some. That's quite a, that's quite a narrow track, and you can move things around a bit and give yourself a bit more space. And there's our V-mid components by the looks of it. It's not too bad. That's the power coming in. See, it would be nice if these tracks were thicker. Like I say, if you set up the class widths for these particular, for these nets, then you can make these fatter rather than make these wider, rather than me doing it manually. I'm just having a look to see if there's any glaring problems. That looks a bit weird. What's all this? There's a funny track. You see this one here. If I just if I turn off the front copper, and I'm doing that on these right-hand side selectors here, and then just have a look at the blue copper. What on earth is this? Actually, what's going on is because it's connecting all the grounds. So maybe what I'll do is I'll do a copper flow for the ground plane, and there's a way to do that. I think I showed how to do that in the previous video. And this funny-looking track will disappear because this will all just be connected. That'll be connected to this through the copper fill. Anyway, it's not too bad. You end up sort of going around the whole thing and just having a quick look, make sure there's nothing obviously silly. We actually have a track that hasn't connected. There must have been a failure. I've just realized something. That pin there is not connected. You see how you can still see the rat line? Okay. Right, so what I'm going to do is I'm going to run it again and see if it picks up on anything else. I'm going to cancel that so it doesn't go automatically. You'll notice it's pulled in what we already had, plus the adjustments that I made. I think, yes, it has. So it's pulled in the tracks that we actually have as well. If you look at the bottom of the screen, one connection not found. We actually have a fault with the board. It wasn't able to route something. Okay. And it gives you a detailed explanation here, which I'm not going to read. Yeah, and it is, I do believe, it would be good if it actually, well, now that pin is connected. That's the one that wasn't connected. So let's do that. Did it fix it? Yeah, well, that's in there now. Okay, that's actually in there. So yeah, it fixed it. Right, so what I'm going to do now is run the DRC, the Design Rules Checker. Now this is a bit like the ERC in the schematic, but this is PCB checking. So let's, this is checking the rules of the tracks and what have you. So let's run that. It's probably going to fail on something. Let's just run it anyway and see where we're up to. We have an error, and we've got 2 warnings. That's not too bad. Let's look at the... Yeah, so there is actually an unconnected pin. See that? Pad 27 of U3. Well, U3 is the controller. Pad 7 is here. Oh, it wasn't pad 7, it was pad 27 by the looks of it. Let's have a look. Run the design rules check now. What did it say? Sorry, my mistake. I'm saying pad 7. It's pad 27, of course, not connected. Right. 27. And yes, you can see the rat line. Now, why isn't that connected? It's got to get to this dip switch here. All right, well, what's interesting is the dip switch is the wrong way around, because all of the grounds are wanted to be down here just to get them out of the way, and it's routed everything through the switch, and it's left itself, because we're only using a 2-layer board. If it was a 3 or a 4-layer board or something, it'd be no problem at all, but we don't really want to go that far with this project and just trying to keep it to a 2-layer board. So yeah, it's got itself into a situation where there isn't really enough room, not without moving everything around. You could do it manually. If I move these tracks down here, I'd have enough room to put a wire in, and I could probably somehow figure out a way around it. But the easiest thing to do here is to actually rotate this. It's basically in the wrong orientation. So let's have a look. But now you see all the grounds are on the bottom. That's much better. So the grounds are on the bottom. And what I'm wondering is, can I just sort of tell it to reroute that? So I'm just going to do auto routing, and I'm wondering if it's going to fix that down here. It looks like it is. I've still got broken tracks. Right, okay. So what I'm going to have to do is do a global clear of all tracks. You can do global deletions and tell it to remove all of the tracks and vias. We're basically going to have to start from scratch. So let's clear. Right, okay. It looks like we've got lots of crossing going over. That's unfortunate. We might have to rethink the dip switch completely. I don't think you can actually flip it horizontally because the component physically couldn't do that. So what about if I rotate it one way? And I want the all of the grounds to be, if I put it back at the side like where I used to have it in the original design, yeah, it means we're going to have a big gap down here. But let's see if the Autoroute accepts that. I'll just save it, and let's see if that cures the problem anyway, just as a test. We should have all the grounds down the right hand side now, and all the left pins should connect to the controller. So far so good, but we'll see how far it gets with that, and see if it can get the dip switch actually connected. But it looks as if it's done it. Do we have any pins missing or anything? Yeah, it's had to do a few vias here, hasn't it, just to get things to connect. But I think it actually did it this time. I'm just going to run it again, see if there was any errors. It would be nice that if it spotted an error that it wouldn't close down the Autorouter. It seems to be closing down even if there's an error. It's not giving us a chance to see anything. You can see down here it actually says Autoroute complete, 0 connections not found. So actually it worked. Yeah, it looks like it's done it, so I'm going to click save to that. So everything is connected. Okay, well that's a good start. It's not very neat. This is a classic example of why, you know, a lot of people say don't bother with autorouters, because you do end up having to go in and, well, you don't have to, but it's best if you do go in and you can just have a bit of a look around and fix things up. And the argument is, well, why bother autorouting if you have to do this anyway? You may as well just do the whole thing from scratch. And I understand that, but you know, it does, for me anyway, it saves a lot of time. And it's also working out things like minimum amount of vias as well. You know, it's looking for the best path with the least amount of vias, and you know that's useful, because if you try and do it manually, you're not always guaranteed to get an optimized result. I guess if you're experienced enough and you've been doing it for like many years, then you probably do get a real sense of. And there's all the grounds as well. Yeah, you probably get like a real sense of optimization. You know, I'm just going around, just clearing it up a little bit. I'm probably going to have to do this again because I haven't done my copper fill yet for the ground plane, which will get rid of all of the ground tracks. I'll save that. That's what we've got so far. Now, if I run the inspector, we run the design rules checker, and run that, theoretically, yeah, we've got no actual errors, but we do have a couple of warnings. Let's have a look. Yeah, now it's warning me that the footprints have changed for, if you can see that, the footprints have changed for the 12-pin header and also for the 2-pin header. That's these two here, of course. And the reason why it's warning me is because I've had to do a sort of a mirror flip, because, and you don't normally have to do this, but I have in my case, I wanted pin 1 to be at the bottom. And if you place the component on normally without doing any rotations or flips or anything, pin 1 is at the top. And I don't want pin 1 at the top. So I've had to modify the headers and flip them round, which you can't normally do, and put pin 1 at the bottom. So it's completely fine, because if you think about it, when you put the header into the board, you know, you could have it pointing this way, you could have it pointing that way, you can orientate it any which way you want, and there isn't any markers on the header either. You just cut them off as a strip with your side cutters. So it's right to warn me that the footprint has changed. It's correct for it to tell me that, but at the same time it doesn't need to, because I've made it that way. I'm going to look at doing a copper fill. I think we're going to go away and do that right now. Right, so we've made quite a few changes. Time has passed. I just want to point out a few things. While I was doing the board layout, there was a few things became apparent. First of all, we didn't have any mounting holes, so I've added those. And those are actually on the schematic diagram as well, where you can see they're all connected to ground as a mounting hole pad. I've also added some text at the bottom here. G0BZY, repeater analog card version 1. And you'll notice that it's in reverse text also on the other side of the board. So if I turn off the front silk screen, that just leaves the back silk screen, and it's in reverse. So when you flip the board, it'll be the right way around. But the other thing was the position of the crystal and its two capacitors, C19, C18. I originally had the crystal over on the left hand side, if you remember, but because I'd reorientated the controller, I forgot to move the crystal. So the rat lines were actually crossing right across from one side of the chip to the other, and that's not a good idea. You should really keep oscillators, and especially things like high frequency crystals, close to the chip. And you can see the rat lines are actually just here. There's a one there going to pin 8, there's another one going to pin 7. But it's always a good idea to leave a little bit of a gap, like here, because you know there's going to be other connections and other pins to connect to. So them's the changes that I've made, and generally just went round everything and tried to get the layout as best as I could. The other thing I've done is I've measured the height of the board with the ruler here. If you select the ruler, okay, or measure tool as they call it, select a corner, and that brings up the ruler, and you can actually select the bottom, and it'll give you the distance. And you can see that's actually 70.485 millimeters. That's the actual length of the height of the board. Let's run the Autorouter and see what we get. I'll do that now. Just click the Autorouter plug-in. Okay, here's our board, and it's going to start, and I'm going to say go. I will briefly mention that I've also updated the class information for the net list for the positive rail, and you'll notice some of the rails are now, some of the traces are now thicker or wider than the others, and those are all the positive rails. So that's the Autorouter using the net class settings that I've put in to keep the traces wider. Now, because the ground traces are shown like here, I hope you can appreciate that when the Autorouter kicks in and does its thing, it thinks it needs to have traces here, so it's going to cause extra work for itself trying to avoid these traces when it doesn't need to, because it's going to have a copper fill. But it thinks that the traces are there, at the moment, so it's having to do things like add vias and whatnot to get round traces that are not even going to be there. So what we can do is, first of all, let's remove all of the traces that we just did. We'll undo that, and you can do that in global deletions here, global deletions, and select, in our case, tracks and vias, and remove. There you go. So now we're just back to rat lines. So how do we get rid of these ground traces? Because we don't need them. It's going to be a ground plane. Well, the way to do that is, I'll just save that by the way. Select a fill zone, and you do that with this here. Control Shift Z if you like. Add a filled zone. So that's what we're going to do. I'm going to hit that. And select the board. Hit the corner of the board. We're going to draw a rectangle. But when you first click it, you'll notice it says what do you want to fill, and we want to do the top copper layer and the bottom copper layer. So I'm going to do top copper and bottom copper. But this is the interesting part. It says would you like to assign it to a net? And yes, we do. If we assign it to the ground net, it means that the copper fill on the top and the bottom is now going to be automatically ground. That's important if you want to get rid of all those ground traces when you do your fill. So let's click OK to that, and now we can continue drawing our outline. And you notice it's kind of going like a sort of a red color, and I'm just selecting the corners as best as I can, and I need to do the top. I'm using the mouse wheel again, and here we go to finish it, and there you go. Now you'll notice we've got this like hash around the edges, and this is our fill zone. Now if you right hand click that hash and go to zones, you can select fill all zones. Alright, and I believe you can actually press B to do the same thing. I'll just double check I'm right in that. Hang on. Yes, you can actually press B to do the same thing. But I'm just going to click this. So this is fill all zones. Let's do that. Right, now you'll notice it's filled everything in. We've now got a copper fill on the top layer and on the bottom layer, but we don't have any traces yet because we haven't run the Autorouter or made any manual traces. But you can still see the rat lines. Okay, so we've got our, they're quite faint. I don't know if you can see these, but we've got you know, we've got our rat lines here. So, but we've now got copper fills, and what it means is things like ground. You'll notice here's a ground pin on our power connector here. It is already connecting them to the copper fill. We've got rid of the ground traces, so the Autorouter has less to do. So what we can do now that we've got the copper fill on the top and on the bottom, I'll just save what I've got there. We can run the Autorouter, and I'll see it do it now. When it does it this time, there are no ground wires to take care of. Everything's already connected to the copper fill. There's less traces, in other words, which reduces the amount of vias and traces required. So that's doing that now. It's pretty quick. That was it. Took about 10-15 seconds, was that? Something like that. And now we can go in and have a look, and there's our traces. Now I'm going to turn off the bottom copper. In fact, I'll turn everything off. Let's just have a look at the top traces here. What it looks like here is that it's done the traces, okay, but these traces are actually merged with the copper fill, which is all this red area here where it's done the fill previously. So now we'll have to press B, okay, which will fill all the zones. So let's press B now. There. Now we've got insulation between all of the traces. And you'll notice the ground is connected to the copper fill. That's perfect. That's exactly what we wanted. You may notice that there's still a rat line over here doing something strange. So we're not quite there. And what that probably means is, if you can see this, it's coming from the copper fill here, and it's coming down to this part of the copper fill, and it looks a bit odd. They're not pins or anything. It means that this copper area here is probably not grounded. You know, because you've got these insulated areas around the copper fill, and you can see, if you look around there, it's insulated all the way around. So this copper fill here is not connected. Now, what the easiest way around that is, all I do is I just put via pins through the board, to connect it to the other side, and then it makes it ground. So if we do that now, I'll turn on the back layer. Let's get a wire pin and stick a couple of wires in here. I'm just clicking them in here. All right, and we'll do B for fill again. Now, can you see that that trace that we had, that rat line, has gone? We've just fixed the connection. Now this copper area here, again I'll turn off the back, this copper area here is now connected through the wire pins to the other side, which grounds all of this area here. So we've just fixed it straight away. So yes, we've got 21 errors and we've got 2 warnings. Okay, now if we go to this tab here, if we go to this tab here, it says unconnected items. Now these are the most important. That means something really isn't connected on the board, and there's a few to sort out. So I'm going to basically rattle through these. Missing connection. Okay, if we go there, yeah, you can see this ground pin here is not connected to the copper fill, which is a little bit odd because it's right next to a ground area here. It just means that the Autoroute didn't regard that as enough to make a trace, but we can just manually bridge it across with a piece of wire, or well, not a piece of wire, with a trace. So we'll go from there to there and do a B, which just refills everything. And if we run the DRC again, let's see if we've got rid of that. It should have done. If this is actually grounded, it should have got rid of that. So let's run the DRC, clear everything, and run it again. Yeah, it's cleared it. So now that marker's gone. So it really is just a case of going through the board now manually and picking out all of the little faults. The Autoroute isn't perfect, especially when you've got, you know, denser areas like this. And I'm only using a 2-layer board, remember. If you used a 4-layer board or even an 8-layer or whatever, you would never have problems like this. It would just sort it all out. But I'm trying to keep this down to a minimal design and minimal cost as well. Just using a 2-layer board is pretty cheap. Spent a little bit of time just eyeballing the whole thing, going through it, trace at a time. I'm reasonably happy we've got somewhere near what we want. This could well be the final layout that I'm going to do here. As you see, we've fixed those violations. Everything's now connected. All these grounds are connected. I've added a few wires here and there to connect the top copper to the bottom copper to sort out the problem with the ground planes. Had to manually put in a couple here just to get things to connect. It's okay to do that. It doesn't look very neat, but never mind. But once it's all fabricated, once the board's made, you won't see those tracks. It'll just be one big copper per area there connecting things together. Yeah, that's pretty much it. And like I say, I've got wires in various strategic places, like here, connecting this top red part to the back blue copper layer there. And what else can I talk about? I've added some labels like CW mute, so you know what the trimmers do, audio level, which is great because when we come to actually use the board, I won't have to refer to, you know, sheets or pieces of paper with things written on. The silk screen is self-explanatory. It really just tells us straight away what the controls are doing, CW level there. Finally, we can click the 3D view, which is from view, and then select 3D viewer. And now we can actually have a look at what the board's really going to look like. That's pretty cool. It's pretty much as we saw before, except now we've got all the traces where we want them. And there's no errors. Everything is now connected. Crystals on the correct side to get rid of the traces. You should be able to see some traces. There they are. They're crystal PCB traces. And then we've got the C19, C18 on the right hand side, which is grounding. They're going to ground. So there's the crystal. We could have maybe got that a little bit closer, but like I say, that's fine. It's acceptable. It's close enough. That's the dip switch for our channel selection. Now you'll notice that the legend is the correct way around here. And if you flip the board to the other side, and there it is again, printed correctly on the other side. That's the mirror text. When you flip the board, then it corrects it to the right size. So there you go. All looks present and correct. I think we're pretty close to actually being ready to send this to the fabrication house. It's pretty much looking good. Can't see any obvious problems. Alright, looking good. So you will notice that I've added some top silkscreen legend to the pinouts. Again, this just makes life easier when we come to wire the thing up. When it's all finished, we're going to have labels, ground, TX, CW and so on, just to make things a little bit easier. There's not a lot of space to the edge of the board, so I've had to abbreviate some of this, like D in is, that's discriminator in, and things. A in is analog in, analog out, detector, all that kind of thing. So yeah, and +5 and ground up here. So that just makes life easier when we come to wire the thing up. So if you then select File, you can go to Plot, which is just here. Select Plot, and then from this dialog you can select which layers you want to export and which ones you don't want to export. Normally the default is quite good. You could switch on all the layers, I guess, if you wanted to, but you know, a lot of them are not being used, like user drawings, user comments, user eco 1, user eco 2. I'm not using any of those, so I really don't need to select them. But the important ones are things like front copper, back copper, front silk screen, back silk screen. Those are the most important. So you can just go down the list. Fabrication, well, they don't really need the fabrication layers, but you can send them, they just won't use them. You know, it's best to sort of like spend a little bit of time, make sure you've got the layers that you've actually used, and the ones you don't use, just untick. So the thing to do is to go to your output directory, and I've got a directory here called Gerber, which will be part of the project folder, the analog card project folder for KiCad. And I've created a subfolder called Gerber, and all of my output files are going to go there. We'll do a plot. This is now going to output all of the files. Plot, and it's creating all of the files, and it's done them. So here's a whole list of output files. There's all the layers that we've selected. These are all GBR files, Gerber files, and there's a project file, a job file as well, which you don't need to send to the fabrication place. They don't need the job file. Everything's green, which is good. We've got no errors at the bottom and no warnings. Now once you've done this, there's something else you must do, which is to generate the drill files as well. Now the drill files, nothing to do with traces. These are where physically the board's going to be drilled and what size holes they want. So you have to export the drill files as well. So click that. Okay, again, it's going to go into the subfolder Gerber. That's where I'm putting all my output stuff. And that's going to be generate drill file. I'm pretty much just selecting all of the defaults here. Haven't actually selected anything here. Generate drill file. It generates two files. One's for plated through hole, PTH, and the other one is for non-plated through, NPTH. So what that's doing is it's created two different drill files. So now that we've got the drill files exported, and also we've plotted out all of the fabrication layers, you know what? We're kind of done with KiCad. That's it. So we can close this down. We can close that now. And basically we can go to our folder with all of the Gerber files in. Yeah, so here we are in my KiCad projects folder. And this has got all my projects in, and this folder here is called the analog card folder, which has got all of the files in. But this is the main PCB card here project, so main PCB project here that we've just exported to Gerber files, and you'll notice we've got this subdirectory here called Gerber, which I created. So all of the output files are here, and this is what you end up with. You'll see there's a couple of drill files at the bottom, so you need those. They've got to be sent. There's a job file here, which they don't really need. We could remove that. And all of these files here, which I'll select, these are all selected. These are all the actual Gerbers. Each layer, like the back copper, front copper, what have you, fabrication, everything. There's the front copper there. These are the actual layers that the fab house needs in order to create the board. Now what I tend to do here is zip them all up into a single zip file, okay, excluding the job file. So I'm going to remove the job file, gone, just delete it, and these are the files. Select all of those and right hand, and what I need to do is output it, send it to as a zip, compressed folder zip, and that's it. This file here has got everything we need. All of the drill files and all of the layers have all been exported and zipped into this single file. So all the work we've been doing to design the board is right in this file here, and this is the file we're going to send to the fabrication house. They'll understand everything from that file. Hopefully there's no errors. If there are, they'll usually get back to you and say you've got a design problem. Send them the file. In my case, dealing with China to here in the UK, the entire turnaround time from me uploading this to them and paying for it to receiving the boards in the post through the letterbox is about 10 to 12 days. That's pretty good for the whole turnaround time from upload to letterbox. It's about 10 to 12 days. Price wise, well, I think the last time I got a board made, I think you're talking about $30, something like that. You get like a minimum of 5 boards, but it really depends on who you're dealing with, and you can probably get them cheaper if you shop around. That's the end of that, and I'm now going to send this off, upload it. There's going to be a waiting process and a huge jump cut, and when we come back we've hopefully got some boards made. Okay, and welcome back. Well, and I'm going to have to figure out how long, because I haven't worked out how long, but it's probably about 10 days. The PCBs have arrived, and this is the wonderful part of looking at the boards for the very first time. I'll see if I can zoom in a bit. It's very well sealed, brand new boards. Yippee! It's always exciting to get new boards. So let's get this open and have a look. Yes, I love new boards. I like them even better if there's no mistakes on them, but never mind. And as you can see, I've gone for green PCB. Check that out. Yeah, looking really good. That's actually the right way around. Check the back, and I've got a little bit of silk screen on the bottom. Quite small font, but that's fine. Green boards to match the 6502 board. So the next thing we need to do is populate the board. So there we go, brand new board. Looking good so far without having a real close inspection. So onward, that's the board. Looking pretty damn good so far.